So when it comes to IT and tech and computers, I am basically somewhat of a dinosaur at this point. I've seen everything that there is really to see with regards towards tech stacks, uh, system architectures, how to go about these things from a large corporate level. And one of the best examples of system performance and kind of like back end system maintenance that I've seen from an enterprise level is the Chaos Monkey model, which was introduced by Netflix. And the chaos monkey model is very straightforward. Essentially, what they do is they introduce random chaos flat out into their computer and their networking environment within their internal workings of Netflix. They purposefully cause problems within their computer systems and for their teams, their internal teams, for them to be able to solve these problems. And the goal is that they randomly throw in chaos monkeys, and then by doing this it trains the team to be able to react to situations very quickly, and then it makes their systems more robust overall is the bottom line. And so to me, it's an interesting concept overall. And so I figured, hey, what would happen if we threw a chaos monkey into a neural network as opposed to a computer network? They operate kind of the same on the same level. So what would happen? And so what I've done is I've created a chaos monkey model. And then so what I've done is I'll go through it, but so it's a normal neural network. And then we add a chaos monkey layer. And then the chaos monkey layer essentially shuts down randomly parts of the neural network during training, and then the chaos monkey decreases over the training epochs. So if we train for 100 epochs, chaos monkey is like all there in epoch 1 and then is gone by epoch 100. It's kind of how that would work right down. And so within this, I've run a few tests now, and in this, we'll look at two data sets. We're going to look at the iris data set and the wine data set, which are very popular data sets for machine learning. And then so in this first instance, we'll look at iris. And then so we just have to set a random seed. I pick 42 because I have to pick a number, so why not pick 42? And then we load our data set, which is in this instance the iris data set. And then we have our test and training data set. And then we want to shuffle the data, pre-process it, split the data into test and training. And then here's our simple neural network. Here's all the parameters of the network. Very straightforward, just normal parameters. And then so we're using ReLU and Atom Optimizer for the training mechanism. And then we're training it for 200 epochs on the iris data set specifically. And then we evaluate the model, and then we get our results. And then so we look through, and then if you're just going through this is exactly what I would expect to see, right? So first of all, off the bat, highlighting, the accuracy starts off very low, 0.24, and then it's a while before it gets to, so epoch 27 or so, we're at 50% coin flip accuracy. And then it starts getting a lot better. It jumps from there, right? So then let's go up to epoch 50. Yeah, by epoch 50, we're almost at 75% accuracy, and then by epoch 200, we're really good, right? Like we're almost like we're peaking at 100% basically. About like if we look at this, about like 160 or so is when we start getting close to 100% validation accuracy. And then we can see that we do have so the model hits a local minima around epoch like let's call it 30, and then it has a little bit of a drop off until and through epoch 50, and then we get that jump starting off about epoch 75, and then we can see that jump in our graph here, right, from about epoch 75 to about epoch 100 is good progress overall. But so this is standard loss and standard accuracy and what I would expect to see overall, right? There's nothing uncommon about this. And then so now let's look at this same exact example introducing our chaos monkey model. And then so the change that you can see here is that we're creating a chaos monkey layer. And then so the chaos monkey layer is, again, it's just randomly shutting off parts of the neural network during training. It's exactly what it's doing. So if it's let's say it's a 200 million parameter model, it's going to shut off 50 million parameters randomly, like during training for few seconds, and that's exactly what Chaos Monkey does in this instance. Everything else is the same, except for we have our some additional logic here for Chaos Monkey. And then we go through and then we run. We can see here, same thing, right? Accuracy starts off very low, 0.225, and then let's look at 25. We're by 25, we're already past where we were at 50, right? Without Chaos Monkey. At 50, we're at almost 80%, whereas we were less than we're at 79% when we're at 74%. So 5% increase at 50. And then let's look at the graph here. Oh, and then so we can see here, big difference, right? So first of all, we're hitting our 100% accuracy over 25 epochs earlier, very consistently. And then we can see a much more consistent climb, like that climb that was starting off at about epoch 75 there. I'd say it's starting off about here, right? So epoch about 30 as opposed to 75, that big climb. And then the big climb doesn't stop in this instance until we get to 100%. We have no local minima. This graph is like, I mean, it's off the learning rate is definitively better in that graph than this, right? We can see we're not hitting here until 160, and then we've got this low stuff here, right? And then so we go down, just again highlighting. I mean, it's pretty apparent to me that this graph is definitively better. There's no contest there. And then so maybe it's just a data set, right? So then let's look at the wine data set. And then so this is the exact same thing, exact same setup, just with the wine data set as opposed to the iris data set. And then so we can see here it likes this data set a little bit better. It starts off at a little bit higher as far as the accuracy. And then I should note too, I'm training on this one for 100 epochs as opposed to 200 epochs, just because the models, as you can see here, they converge on this a lot more quickly, and they understand, like, this is just a better data set for them to understand overall. And then so what we can see here is this is the without Chaos Monkey, just our standard model around epoch, let's call it 40. It gets up to 100, we start getting up to 100% validation accuracy, right? And then so that's why I'm only running it for 100 epochs. It would just be even worse than this. So it's pretty straightforward, right? It climbs up pretty quickly. This model understands this data set very straightforward, very simple. Like, this model is understanding this data set. It's kind of the bottom line here, right? And then, but so we can still compare it to our Chaos Monkey. And then, whoa, we can see that there is a massive difference here. So epoch 20, we'll call it, as opposed to epoch 40 here, right? It already hits here. And then it's just, I mean, boom, 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 right? So even with this data set, even though it's learning on this far more quickly, we can see that the model is converging faster with the Chaos Monkey as opposed to without. And then so to me, it's just interesting experiment overall, right? I just playing around with this, I figured, to me, how I came about this and I thought about this is, so models have an overall problem with generalizability. That's the biggest problem with the models, right? And then so to me, I think the biggest way to solve that, just flat out, the way that my brain goes to, is to introduce adversity to the model, and overcoming adversity is, to me, the best way to train generalizability. And then so simulating adversity, I come up with the Chaos Monkey example, and then throwing in Chaos Monkey into the neural networks, giving it a try, just experimenting. Hey, what's going to happen? I had no I didn't know if it was going to be positive or negative on the impact on the model, right? Going in, I was expecting, my initial hypothesis was leaning slightly that this would be bad for the model. I was slightly surprised when this ended up being good for the model overall. But I still thought it was worth experimenting and going through the experiment and going through that exercise. And to me, I'll end the video here and highlight that, right? So if you wonder, like, how do I think of these things? How am I going through and figuring these things out? It's just experimentation plus 25 years of IT knowledge plus a bigger fact, and I think it's important to mention and state this within this. So Jeffrey Hinton just recently won the Nobel Prize for Physics, and then so there's debate over that, right? Should he have gotten the Nobel Prize for Physics? In my opinion, 100% yes. Jeffrey Hinton 100% deserves the Nobel Prize for Physics. And how I honestly go about a lot of this, and I think of through, and I go through a lot of this experimentation, is I marry computer science and physics flat out. I've been interested in physics and quantum physics and everything around it ever since I was a child. And then so that knowledge and all of that that's associated within that 100% plays into my experimentations with AI. And so to me, AI is a subset of physics, flat out. It's impossible at this point to separate the two. If you understand what's going on mathematically with these models, how exactly we're going about it, I mean, it's just flat out fusion of physics knowledge and computer science knowledge at this point. And then to me, playing around, throwing in a chaos monkey and seeing what happens. That's literally how we're progressing, but it works and it's fun. So if you like this type of content, please like and subscribe. Thank you very much.